Great. All right. Thanks, everyone. And thank you for joining today. Today, we're going to be having the first of this year's webinars on digital manufacturing cybersecurity. The topic today is on mechanical compromises and defect detection. My name is Hammond Pearce. I'm a research assistant professor here at New York University. And I'm also going to be the host and moderator of this event. First, I'd like to acknowledge our sponsors, the National Science Foundation, and of course the NYU Center for Cybersecurity, who make these kinds of events possible. So a brief introduction for this topic. Traditional manufacturing is increasingly being supplanted with new technologies. Factories are becoming smarter and more interconnected, and new hybrid techniques are increasingly being adopted, such as 3D printing and smart hybrid manufacturing. With these new advances in manufacturing come new risks, especially given the cybersecurity domain. Across our complete series, the NYU Center for Cybersecurity is going to be hosting 4 panel discussions with experts from academia and industry. All of these events are recorded and will be put available on YouTube. But most of all, these panels are an opportunity for you to directly ask questions to some of the leading experts in the field. It's our hope that the conversation that emerges from these events can inspire some future research efforts in this area, and also to introduce new and interesting ideas to all of our attendees from academia and industry. This is the first webinar in the 2022 series hosted, this is actually our 3rd year. So this is the 3rd time we've done these series. Our first topic this year has a focus on detecting mechanical compromises and defects, such as what are some of the ways that parts could be maliciously edited to cause reduced performance or failures? And likewise, how might we prevent or detect such failures in any given digitally manufactured part? This is pertinent because as manufacturing becomes increasingly online and more interconnected, the risks of cyber attack grow. And as we've already seen from several high-profile attacks, cyber attack vectors are beginning to be exploited. We're very fortunate today to have 3 eminent panelists with us. I'll briefly introduce each, and then each of them will take over and talk a little bit about themselves. Oops, there is a mistake on this slide. The first panelist is actually Dr. Guha Manogharan. I don't know why it's his Kyle, that's a mistake, pardon me, who's an assistant professor of mechanical engineering from Pennsylvania State University. He heads the System for Hybrid Additive Processing Engineering, which focuses on additive and hybrid manufacturing with an emphasis on biomedical, defense, and aerospace applications. Professor Guha received his PhD and MS from North Carolina State University and was awarded the 2021 ASTM Emerging Young Professional Award, 2020 NSF Career Award, 2018 International Outstanding Young Researcher in Freeform and Additive Manufacturing Award, 2017 Society of Manufacturing Engineers Awards, and some other awards as well. Very distinguished guest. Secondly, we have Joshua Lubell, who's a computer scientist with the National Institute of Standards and Technology, whose work focuses on smart manufacturing systems cybersecurity. His technical interests include markup languages and information modeling. His baseline Taylor software tool for security control selection won an award from Government Computer News, and he is also a past winner of the Department of Commerce Silver Medal for his leadership in developing ISO 10303-203, a standard for representation and exchange of computer-aided designs. Finally, we have Dr. Luke Boyer, the Manager of Additive Manufacturing Operations and R&D at the Emerging Technology Center for Carpenter Additive. Luke leads an agile R&D engineering group and manages AM powder-to-parts operations for industries ranging from aerospace to medical. Prior to joining Carpenter, Luke was at Baker Hughes, where he helped found and lead the first additive manufacturing group and grow it into a global R&D manufacturing operation. Luke received his PhD in Materials and Nanoengineering from Rice University in Houston and his Bachelor's of Materials Science from McGill University in Montreal. I'm really pleased to welcome these 3 panelists. So what I'll do now is request each panelist to take just a few minutes to give an overview of their work related to this area. I'd also like to mention to all of the attendees, from now, you can ask any questions using Zoom's Q&A functionalities. And what will happen is those questions will then pop up to me and I can ask your questions to the panelists. So without any further ado, let me hand over to Professor Guha, and he can introduce himself and some of the areas in which he's working.
Excellent. Thank you. And just for the record, I'm not Kyle. Uh,
Yeah, sorry about that.
no worries. I'm Guha Manogharan. I'm going to share my screen and let me know if you can see it.
Yeah, looks great.
Excellent. I had the systems for hybrid additive process engineering. So I'm going to give a quick overview on some of the processes that we have been working on. We consider ourselves to be an experimental manufacturing group here at Penn State in year 6 now. And Penn State, I'm very proud to say that additive manufacturing, we are one of the leaders in terms of not having additive manufacturing within one particular department, but we have folks from all different departments. In a center for Sim 3D, and we also have the Masters in Additive Manufacturing and Design, and it is 5 years strong now. I think we have over 185 students in the last time I checked the number. So I'll briefly give a couple of topics that are active research areas right now, in addition to other laser powder bed. So we are expanding into a binder jetting system. So emphasis here is being able to control the pore networks, or try to control the pore networks, and understand the fundamentals of multimodal powder size distribution, and also binders with suspended nanoparticles for densification for different application domains. Again, we look at everything as a manufacturing research question that can solve problems across a gamut of applications. One application could be right now is an hypersonic missile materials, where we are trying to get the best of both ceramic and metals, where we are trying to print these network pores in alumina or other refractory high temperature ceramic, and infiltrate it selectively with metal, so you get the metal matrix composite. We're doing some work with a colleague of mine on molecular dynamic simulation of understanding the time temperature sintering profile of these new materials, new binders, and so forth. Some of our other topics include post-processing, and I chose only few slides from our research portfolio of topic of relevance to today's discussion, because post-processing is a big element of detecting defects, and also keeping track of where your parts are, how it is deformed, and also for example, we have some ongoing projects with nuclear engineering department in trying to make sure that each of the part is very unique, that is printed for a nuclear reactor component or any other high performance and high security applications, but leaving signatures in them so that we can track the location of the part every time, and keep track of it. We do quite a bit of work on post-processing, and specifically on CT scan as well, coming up with new CT scan protocol for additive manufacturing, specifically metal AM. And I have only two more slides so that I can yield the rest of the time to my co-panelists. So here is a very broad snapshot of some of the other projects that we have going on. We are very active with biomedical applications of AM, with what we call as biomechanical biomaterials, where we're trying to mimic the topology, the mechanical properties, the morphology of the pores, and the surface roughness that could promote, or that mimics that of naturally occurring bones. So that is on the direct metal AM side. We are doing some work on orthotics and other applications using digital light processing, and 3D sand printing is a big part of our research portfolio right now. It costs around $15 to $17 per cubic inch of printed titanium, and it costs 10 cents per cubic inch of printed sand. And you have 225 alloys that have gone through MMPDS, the material qualification for DOD for casting, whereas there is only two that have gone through for direct printed metal. So again, there are pros and cons on different applications of additive manufacturing, but I consider 3D sand printing and printed shell through digital light processing for investment casting as the indirect metal AM, where we are using AM as a means to coming up with tooling that is used for making metal parts. And I want to thank some of our sponsors right now: NSF, AFRL, DOE, ONR, and so forth, and manufacturing P. And I want to leave with this particular slide. And whenever I talk about additive, I always bring this up at a talk or panel: when to use additive. And I want you to everyone to pay attention to the three axis labels. One is production volume, not size, but number of parts. The other one being complexity. Keep in mind the complexity could be from the design and or the material. And customization. So how many of these needs to be customized depending on the part size. So we preferably want to check all three boxes, where you look at number 8 right here, which is highly customized, highly complex, but you can have mass manufacturing. So is this where additive is? So again, I think of the Invisalign brace as a good example. It's highly complex design, highly customized for each user. And they sell, like, I think last time I checked, it was like 22 million units or something. Guess what? They do 3D printing, but not printing of the brace itself, the tooling for it. So I'll leave with this particular slide in terms of checking boxes when additive manufacturing is good, is ideal. So with that, I will stop here, and then I have backup slides as we go along with the panel chat. Thanks for the invitation, Nikhil, and thanks, Hammond, for QBing the panel. Thanks
so much, Professor. For the next introduction, can Joshua, can you share your slides and just briefly introduce your work?
Yes. All right, can you see my slide?
Yes, great, thank you.
Okay, great. So, yeah, thank you for the introduction, Hammond. Just a little bit more about me. For the last 8 years or so, I've been involved in cybersecurity, and I came to that from a prior background on supporting product data standards development, most notably STEP ISO 10303. And then in the last 3 years, I've became more interested in additive manufacturing security, and now my focus is gravitating more and more toward additive manufacturing security. And all of this is colored by a longtime interest I have in markup languages, XML and its alternatives, and data modeling. And just on the right-hand side of this slide, I have a couple of screenshots of some prototype tools I developed that help digitize cybersecurity guidance and make it more useful and in terms of making it actionable in applications, or in the bottom right case, being able to fuse different types of guidance together to create a sum that's really bigger than all of its parts, if you will. So essentially what I try to do is connect the dots between the security guidance that's out there, like the ISO 27000 series, and also the NIST risk management framework, which are very broad general guidance that's highly useful, but is not specific to any particular discipline, and then try to address the issue of how you apply this to something very specific, like a 3D printer. And turns out that there's a lot of concern, a lot of issues about that. So to give you an idea, in the kind of the typical methodology for enterprise IT security, there's the notion of a specialized security limited functionality system. And this would be a system that must be highly secure, and therefore what you do is you emphasize security more than functionality, so you only allow the functionality that it's concerned with, and then turn off everything else. So for instance, you might have a single software application that's mission critical and needs to be protected, and therefore you do not want to have lots of network services enabled. You don't want to be able to run a web browser or do email, etc. And similarly, the kind of best practice is to take such a system and segregate it from other systems on your network, so that an infected system outside the zone in your network can spread to this system. So this is kind of, it's a long established idea, and at least in principle, it's pretty simple. But when we get into manufacturing systems, then there are all kinds of complications. One of which is, what exactly is the system? Is it just a single piece of hardware, or is it the supply chain that it's part of, or is it, or maybe it includes the machine and then a host computer or, you know, and what about a digital twin? So there's defining what you mean by a system matters a lot. And then also there's the issue of what functionality can be limited. It's beyond the standard best practice. You can't really limit the functionality of the machine without limiting innovation and limiting its capabilities. So you have to look more closely at what the machine actually does and the information that it processes, and that knowledge has to inform your security approach. And that kind of knowledge is not part of the general guidance. So there's more work that the manufacturing community has to do to account for that. And then lastly, a lot of the existing guidance out there implies, you know, network-based enterprise management, but what about direct attacks on hardware, like a side channel attack on a 3D printer, for instance? That is not within the scope of the SSLF, you know, typical guidance. So that's it for my introduction. I just wanted to pose some questions and kind of give you all a sense about the problems that are unique to manufacturing and how those have to be taken into account when developing a cybersecurity program.
Great, thanks so much, Joshua. That was a great introduction.
Thank you.
We now have Luke. Luke, can you briefly do your introduction as well?
Absolutely. There we go. Thanks. So as with, can you see your pictures as well, or just the screen?
Yeah, we can see your slides. That's great.
Just slides. Okay. So yeah, thanks Hammond, and thanks Nikhil. I really appreciate the invitation. And yeah, obviously some really impressive work that's going on by Guha and Joshua. So I'm part of Carpenter Additive. Carpenter Additive is kind of a daughter company of Carpenter Technology. It's a 130-year-old company, works in the material space. You can see the product form over on the left side. It's powder, ingot, strip, wire, bar. It plays in all the spaces. Alloys are generally the higher end alloys. So your cobalts, your chromes, your nickels, your stainless steels. Yeah, pretty much all of that. The market is really in all the spaces. Aerospace has conventionally been kind of one of the larger areas where we work. And then the growth platforms, as you can see over on the right-hand side, are really additive and electrification right now. So it's obviously that's kind of what we're talking about today, and that's where I'm coming from. If we look at again some of where we're looking at to grow innovation-wise, the spaces where I play is in both the powder metallurgy as well as the additive manufacturing. So we have atomizing capabilities in 3 different locations globally. The largest domestically is here in kind of the Huntsville, Alabama area, just across the wall from where I'm at in the Emerging Technology Center. We have a team over in Liverpool, England, does some of the earlier stage tech development for additive manufacturing and kind of lower to mid TRL for powder atomizing, in addition to our R&D facility that's in Reading, Pennsylvania, which is the Carpenter Technology. And yeah, like I said, I'm down here at the Emerging Tech Center, which is where we do all of our printing, as well as any sort of applications development. The building over on the left-hand side is the ETC. It's the same one that's behind me, but maybe mirror switched. The Additive R&D Center of Excellence is effectively where I am within that ETC. Carpenter, again, you know, pretty rich history, extensive experience in the metallurgical arena, and and especially in powders when we look at additive manufacturing. So where we're at right now, we have a program that is branded under the name Powder Life, and really it's looking at the entire production thread from atomizing all the way to the part production and trying to connect the digital thread. So obviously, when you start talking about connecting digital threads, something like cybersecurity starts to hit pretty home, pretty close. And you know, and the comment there on the left, right, one thing that we're seeing time and time again is that really cybersecurity needs to play an integral role in the digital thread and considered from the onset, not just as an afterthought. So, you know, during these implementations or idea consumption, the cybersecurity experts are pretty key stakeholders and not just solution providers on the back end of implementation. So wanted to move that pretty quick, just you know, so we can kind of get on with the meat of the conversation.
No, that's great. Thank you so much, Luke. So what we'll do now to all the attendees and to the panelists is we're going to move into an open discussion format. So that means that you can put your questions into the Q&A box on Zoom, and we have some questions of our own as well, and we'll use that to sort of frame the discussion. So actually the first question's already come in from the audience, and it's to everyone. And it just it's along the lines of, within your work and research areas, what are some of the different detection techniques that you might use to detect any kind of anomaly, whether that's in your powder or that's in your parts that are being, you know, that are ending up in your different domains, such that you might be able to detect, you know, any kind of malicious action in the design or manufacturing times? So that question's to everyone. So I'm happy for anyone to go first.
I'll go first. I think that's a really good question, and I'm glad that you the attendee thanks Seng for the question. Distinguish the design and manufacturing. So there are opportunities for malicious modification, both design as well as in the manufacturing. I'll talk about the design aspect first, and I'll have my co-panelists talk about the manufacturing if they want. On the design side, definitely keeping a standard digital firewall for your file. I mean, that goes without saying, but also specifically looking at the file format. Some format are more robust than others, and depending on which software you're using to design your part. But I always believe that regardless of whichever protocol that you have, always to go through the slices and not just take the CAD file, slice it and send it right to the machine. If you typically do simulation on the design side, if anything is off, you should be able to catch it. And there are other techniques in the manufacturing side, but I'll let my panelists chime in for that.
Yeah, so I can add. So, you know, from a physical perspective, right, there are certainly a lot of processes that we have in place. We do work with some controlled materials that are classified as such by the government, and there are guidelines for how those are handled and how those are stored, who has access to those rooms, training by individuals, etc. And then on the other hand as well, there's also kind of an attempt at instead of having a mitten, if you will, for like kind of a cybersecurity individual basic, it's more of a glove approach, right? So wherever there's any sort of activities or opportunities for a computer to be plugged into a network somewhere, it's instead of having one fence everywhere, right? You kind of bring it in the perimeter, if you will, closer to those machines. How that's done is I have no idea, but that's the that's the general philosophy.
So here's another question. Cybersecurity is often considered as a topic for computer scientists, which seems fair. Given what we're coming from the manufacturing domain perspective, do mechanical and material engineers have a role to play within cybersecurity?
So yeah, so I'll start off with this, unless Joshua, you came off mute, so if you want to jump in.
I just wanted to, speaking as a computer scientist myself, I think we material scientists and non-computer scientists must have a role, because otherwise what's left is IT, enterprise IT system security, which is clearly insufficient. And I think specifically if you look at additive manufacturing, there's a tremendous amount of potential attack vectors, because you have the variability in feedstock, different printing technologies, and then within a single printing technology, there's a series of slicing steps, so there's multiple places, some digital, some analog, that are that provide avenues for attack, and also avenues to detect against attacks. So for example, there's some mechanisms that can both be an attack and a defense mechanism. For instance, side channel, you can use a side channel measurement to create a baseline of a part, and then by the same token, a side channel can be done to steal data used to build a part as well. So there's definitely I think the mix of disciplines has to come together, and I think in working at NIST, we have a lot of very smart people working on security, and we also have a lot of very smart people working on additive manufacturing research, but I don't think we have, I think we need more cross-pollination between the two disciplines. And I think that doubles for other kinds of manufacturing as well, like CNC and other industrial control systems. So I think there's definitely a need to come together and to connect those dots, like I said in my intro.
That's great, thank you. We've got a few more questions coming in. So here's one for Professor Guha. You mentioned in your introduction that your research involves composite materials and new types of materials. What might defects look like when considering these new materials and their microstructures? And if you're doing materials engineering, what does a defect look like on that scale?
Sure, that's a good, excuse me, that's a good question. And to start off with, it depends on the AM process that we are going to use. And I'll just use laser powder bed as an example for now. This might also touch upon some of the topics that Josh mentioned, which is always have a very strong SOP and documentation for everything from your powder supplier, and particularly if you're doing new material, looking at the powder size distribution, looking at the chemistry. Since you're doing it for the first time, it would be new alloy that we have not tried printing in the past. So always keeping tabs of vials of powder before and after printing, just to keep track of oxygen pickup and so forth. And also see if some powders, depending on if you try to do fancy stuff like different powder mixing, trying to print them, the flowability would be great the first 2 cycles or 3 cycles, and then you would see oxygen pickup and agglomeration and things like that, even in spite of, like, proper sieving. So that's on the powder side. And on the processing itself, I would say the standard operation is coming up with the build design of experiments to narrow down your AM process parameters. These days, we have a lot more modeling techniques than it was when we started out, where it was purely experimental material development. But now we have ICME and CalFAT that are pretty well adapted for additive for the most part. And looking at the easiest one is to looking at Archimedes density. That's an easy one before we go into CT. And I always recommend printing witness coupons, regardless of your builds, as like 10 by 10 millimeter cubes, or like sticks, depending on how tall your build is. It lends itself really nice to pot both of them at the same orientation with X, Y, and YZ in the same pot, polishing, doing quick microscopy. And the one quick thing I would also add is, like, these days there are a lot more validation that have shown nano and micro hardness comparable to the all pitch effect or the anisotropy in metal AM. So we always do quick Archimedes mount and polish, do SEM, EBSD, XRD, nano harness, save coupons for micro CT after we do the tensile coupons and stuff. Hopefully that's just like the standard material development protocol.
Mm-hmm. And just to build on that, and I think this is a question for both you and Luke. In like the contemporary additive manufacturing space, is it more reasonable to assume that a defective part has been caused by poor quality control? Or, is it reasonable, at what point do we say this is poor quality control versus, someone's tampered with this?
Luke, do you want to go?
Yeah, sure. So, I mean, it's a good question. It depends on where in the process that you're picking up the quality defect, right? I mean, from a manufacturing perspective, I think what I've generally seen is that there's still 100% inspection, and those could be through whatever sort of techniques, right? There are probably a few manufacturers that are moving towards batch sampling for their inspection, but it's always, you have inline as well as final. So probably depends where on the inline inspection a defect could get picked up, whether or not you could say that it's been tampered with. And maybe Guha, you have something to say about this, but maybe if I suspect, and this is full suspicion over here, that if you see the same, probably it depends whether or not you're seeing the same defect over and over, or if it's some sort of defect that seems to be randomized. What are your thoughts on that? Guha?
Sure, that's a really good question too, and I'll add to what you added, Luke, which is one, looking at not just where the defects is, but also the type of defects.
Mm-hmm.
Some of the defects, depending on the geometry, you can attribute them to keyhole deep, because of energy density or poor recoating or poor flowability. And the other thing I will quickly mention is not just the shape of your defects that will give you an indication of whether it was because of trap gas or lack of fusion defects, but for the most part, I wouldn't say every machine, but for the most part these days, almost all metal AM providers come with in-process monitoring. Yes, the machine learning methods are still developing, and we're collecting a ton of data for every build that we do in our powder bed machine here. We collect optical images, total of 3 before and after with lighting at different angles, so we get the entire bed before recoating and after melting, and before the next layer. We collect acoustic data, we collect thermal data, we collect a whole bunch of data. So if somebody is trying to change anything in our path planning, you could catch it there. And there are some studies, and Department of Energy in particular has funded some of these work for other groups as well, in purposefully embedding defects and seeing if your sensors can pick them up, and then being able to correlate that with your AM conditions. And the last thing that I would say is it goes back to your file that you start with. And this need not be even for metal AM. I can give like regular desktop material extrusion, filament printing. There are some files that you'll see in GrabCAD or other places that, it's like, a democratized CAD platform. You can get a lot of files, but it would look great in the STL viewer. But I literally have some examples that you can look for, like the die example, where there is missing layers. And so it starts with your CAD file, then locking your machine with your control software, having a standard SOP for your build setup, in-process monitoring, and collect as much data during processing, even if the sensors are there, if you have the computational storage space, and if the program allows you to. I would always recommend collecting those in-process monitoring, because you can always do postmortem on them.
Yeah, so actually I want to build on that. I have another question for Joshua, but I want, just because of what you've just said, I want to do this one first. So you've mentioned there's a few different techniques you can use to detect defects with regards to all of the sensor data and things like that. When you yourself are analyzing things, do you prefer the destructive or the non-destructive techniques? And what are some of those techniques?
That's a really good question. I believe in both in terms of your application needs, but non-destructive testing, if the part is going to be put in service. We are not a service bureau, but I always believe in witness coupons regardless of the build. always have, cubic, like or a square cross-section witness coupon such that the cross-section is big enough. I mean, I think it's like 25 by 25 millimeter. It's the smallest to get the ASTM subsample, subscale sample. Collecting powder. So in terms of destructive testing, we do mechanical, tensile, micro hardness, fatigue, 3-point bending, 4-point bending, impact. In terms of non-destructive, micro CT, I have a collaborator with whom we have just started work on using ultrasonic techniques to detect purposefully embedded defects and see if we can catch it in an ultrasonic sensing. And I know others who have done eddy current based simulation. And on the powder, I would say, looking at the chemistry, powder flowability, morphology, and on the microstructure, grain size, grain orientation, grain density, residual stress, and those things would give you information you need for plasticity modeling.
Great, thank you. So you mentioned, and this is where I'm going to pivot back to Joshua, but you mentioned one of the things that we can do is actually protect our initial data files as well. And Joshua, you mentioned that earlier on in your career, one of the things that you worked on was, contributions to things like the STEP format for CAD files.
Yes.
What are some of the things that, a modern, where are some of the directions we can take CAD files so that we can try and protect them better, I guess is the question.
Well, I think one area that I'm aware of that I know some of my colleagues have done research in is attaching, standardizing or revising the standards such that you can attach digital signatures to your design data or maybe parts of your design data. So having the interchange format better support those kinds of things.
Joshua, can
Yes.
I build on that?
Yeah, sure.
Is that, and I may stop me if I start to sound a bit ridiculous over here, but are we starting to kind of go down like a blockchain sort of conversation or type of signatures, if you will, digital signatures? Is that where you're going, or not?
I wasn't planning on going in that direction, but that is something that folks
like
are
a way to do it.
Folks are very much interested in. I know, for instance, people in the defense industrial base, or a number of them are kind of interested in blockchain technology as a possible way to make supply chains more secure and promote trust between different tier suppliers and OEMs and so on.
I mean, it's a pretty hot keyword these days, right? What's your professional take on it? Because you have a lot of people like myself who will say it, oftentimes out of context, right? But what's your general take on it? You think it's a good future there? That's a good direction. It's just one direction of several.
I think the buzzword blockchain is, I think people pay more attention to that than other things that matter at least as much, like governance. It seems a big stumbling block is who's on the one hand, nobody wants one entity to be in charge of everything. Yet if it's truly distributed, then there are their energy costs and there are trust costs too. And so I think there's a big governance issue for in any kind of distributed ledger sort of architecture. And then the other thing I've heard is that that distributed ledgers in and of themselves are nothing new, that they've been implemented using other ways. So at least from my exposure to blockchain, I think most of what I hear when people talk about blockchain is that we want to have a distributed ledger where there's a trusted party in charge and a way that we can all work together without divulging too much of our IP with one another. And
Yeah.
I think that's more of a, it's not really about the blockchain technology. It's more about other concerns. At least that's my take on it.
I want to just do a bit of a divergence here, because there's a couple of related questions that have all appeared in the Q&A thing now, and they're to do with the side channels. So you mentioned them in your introduction, Joshua, and
Yes.
also Guha's mentioned them as well with regards to the acoustic side channel being captured. So the general question is, there's a whole lot of academic work that's talked about leakage in side channels with regards to video or audio monitoring, but when you talk to people in the industry, it's those threat vectors aren't necessarily considered maybe realistic or serious enough to consider, actively defending against them. So what's the gap here between, why we can see these, coming from academia, why we might think these are a threat versus, what industry practitioners are seeing and doing? I guess this question can be for anyone actually, because we've all sort of talked about it.
If I can say one thing about that, which is I think regardless of whether side channel attacks are just a theoretical thing or whether they're actually going to happen in large numbers, because nobody knows at this point. I mean, I think you're right that most of the work is theoretical, that people have proven that it can be done, but there's been no reported instance yet of anybody who's successfully done one and achieved some attacker goal doing so. But I think it's worth studying, if nothing else, that I think has a lot of potential as a detection mechanism, since one of the nice things about side channels is that you can detect all kinds of information from various other points, that including more plausible avenues of attack, like if a CAD file has been manipulated in some way, that can be detected by doing a side channel of a part being printed with that manipulated side channel, with that manipulated CAD data, and then comparing it against the side channel measurements of what's deemed to be a correct part. So you can measure one against the other. So I think side channel analysis is very important for that reason alone.
That's great, thanks. Did either of you want to build on that answer?
I'll quickly add to what Josh said. I think of it as, having a leak in your basement. You might think, oh, you're just get a little bit of water, but once there is a leak, you just don't know what else could happen, right? So I mean, Josh hit a really good point, which is it's not just for recreating a part using sensor data or acoustic data, but also it's a very valuable tool for part monitoring, in-process monitoring. And there are some efforts that are out there where they're just using acoustic and acoustic of the stepper motors in polymer AM, if people can reconstruct. So I think it's, I'll go back to the small leak, small hole that you have. If you can listen to it and reconstruct the tool path, there are a few other things that you can do, but definitely it is not something that we should keep our eyes off. And I think that is something that we should continue to do.
Okay, I have a couple of questions here for Luke. What order should I do these in? So the first one is, Luke, we can understand that there's probably some limitations on what information you're able to share with us. But do you have any examples of real applications of your powder life or additive manufacturing, or in any sectors where the IP is particularly valuable and you needed to make conscious decisions about how you are going to protect that manufacturing or part data?
It's a great question. I probably have to chew on it a little bit, or talk more generically about it in a different form. Yeah, maybe in a different forum as well. So apologize, but whoever asked the question, if they'd like to reach out to me individually, I'll be more than happy to dig into that a little bit.
Okay, as a separate question then, this is from a different audience member. Are you using the digital thread in Powder Life to detect defects on the fly during processing?
So there is a piece of, so from the software side, not at the moment, though it's on, it's in the vision, of course, on the roadmap. From the hardware side, we do have some tech and some IP that is coming online, whereby we're able to detect chemical changes, in particular, like oxygen pickup, right? Not at a bulk state, but at the particular level, particulate. And we're currently seeded a couple of those units. We're still in the data collection phase, but that's probably, yeah, TRL 4 or 5 right now. And the ultimate vision is to be able to do some of that analysis on the fly.
That's great. And building on this question is another one. Are there specific processes that we're trying to protect in the creation of metallic powders?
So I think most of that is probably down to the physical stage, or the physical processing of it. There are a couple of different manufacturing methods for creating powder. And there's even, of course, the supply chain before the powder atomizers, right? I guess that's it. Yeah.
Okay, that's great. This is another question for Joshua. In the beginning, you were talking about your security limited SSLF paradigm, I guess, if you will. But that paradigm seems to be at odds with, say, the Internet of Things, or these other things where we want to embed computers and everything that can do anything. How do we reconcile these two different, I guess, schools of thought, where one says, if we put as much computing power into anything, then that gives us all this extra flexibility and stuff, but versus, taking the security angle and saying, well, actually, you shouldn't be doing that. You should put as limited computing power in and, as limited connectivity as possible.
Yeah, that's a very good question. And I don't have a really solid answer for that, except that I think we need to make more risk-informed choices in going into the Internet of Things. How important is it that my refrigerator be internet enabled, or that my thermostat be internet enabled?
Mm-hmm.
Maybe, and if it is, am I willing to pay extra for security? And I think part of the current problem is that there's a marketplace full of these internet-enabled devices, such that people don't have to pay extra for security because they want the functionality and they're not thinking of the security. So I think there needs to be some education, some consumer education, and also it would be great for there to be some standards that device manufacturers could be measured against on how they label their products, and and they're upfront about what the risks are, and how buyers of those products are protected against those risks. Because right now we don't have that.
Mm-hmm, mm-hmm.
So I think I'd really like us to move in that direction.
Yeah. This is a question, I think, for Guha now, and we've sort of got two related questions, so I'm just going to try and merge them together. So Guha, you mentioned that for instance, your nuclear printed parts, you embedded codes in them so that you can, unique codes so that you can track them throughout their life cycle. What kind of techniques exactly are used to secure these kinds of parts against counterfeiting and overbuilding attacks, and how sensitive and how accurate are those techniques for detecting those codes?
Sure, yeah, that's a good question. I won't go into the specifics for obvious reasons, but I can say that, and there are some literature out there already out on how to do some of this with particularly metal parts. I would say you can do it in one of two ways. Predominantly, in terms of principle, is changing the chemistry at certain locations, strategic locations. That's not going to change the functionality, and changing allowing at certain locations for certain reasons that can be detected, both using optical and otherwise, using other kinds of non-invasive characterization techniques. So one is on the design, on the material design side or the material chemistry side at strategic spots, and the other one is on some of the design aspects as well. So there are things that we can do with some of the designs that is not visible to naked eye. So I'll leave it at that.
And I guess sort of working with everyone here is there's going to be a lot, there's been a lot of changes in manufacturing as things like digital manufacturing and additive manufacturing have come in. And there are other big changes also coming in, which I sort of alluded to even in the introduction to this whole panel series. So, we've got things like Industry 4 and Industry 5 coming in. And in general, is industry ready for all of these kinds of big changes that are coming on the horizon with the, with the rise of manufacturing as a service and all these other big paradigm shifts?
I can answer that. I don't think so. I don't think they're ready for it, right? Oftentimes, as I mentioned in the intro, right, the cybersecurity team is brought in not when the big operations are set up and they're in the planning phases or program, right, in the planning phases of the programs, but brought in a little bit late. And the knee-jerk reaction, just as Joshua alluded to, is to lock it down and limit the functionality of whatever it is, just to the basics of what need to be done. But in doing so, you lose flexibility of being able to change and implement new learnings and techniques as you grow and make new interconnections and such like that. So, in that regard, there's almost a maintenance, right, that's required to the cybersecurity to adapt and change the kind of overall plan of it, if you will. And so again, it's sort of, the approach today is to bring it in and lock it down. And once you lock it down, there's a great reluctance to unlock it.
I'll add one more thing to that, to what just Luke said. I think part of the challenge and opportunities, but mostly challenge with as an answer to this question is, if you look at the old stakeholder or the old landscape of additive manufacturing, starting from the feedstock, the CAD, the machine, you name it, and all the way through post-processing, in my mind, every aspect of the Lego set, if you look at all of additive manufacturing, everybody's trying to improve their machine, everybody's trying to improve their powder, everybody's trying to improve their software, sensing, and so forth. So it's a very dynamic system where if you certify a machine material for one particular application or one particular domain, you're locked in. So that is going to be some of the challenges that we're going to have to overcome in the next, decade or more. To how do we capture all of this and still not have to go through like 3-year, $5 million certification for every time we come up with new stuff.
I'm glad you've brought up the sort of like future directions here, because for the, we're running pretty close to time here. So for the last question, I'd actually just like a perspective from each of you with regards to your thoughts on how the next generation of students and interns should be, what should they be thinking about? What should they be focusing on? We've got quite a lot of students in the audience, and I know that the YouTube videos are also watched by quite a large number of students. So it would be great to hear your perspectives from each of you about, what are some of the things that people should be focusing on when they're entering into the mechanical engineering or cybersecurity fields, and how would you like to see them impact the field, and what would you like to see them having, grow throughout their career and things like that? So I'll try and get this perspective from each of you, but I don't mind which order you go in.
I'll go first if that's okay, because I just recently had a conversation with some students for our recruiting stuff here at Penn State. So one thing I would say is, whether regardless of whether it's mechanical, cyber, or you're from biomedical materials, pick a strong suit, in the sense like pick play to your strengths and its application or its role in additive manufacturing, and get started on some projects. For example, I'm just going to assume, let's say your strength is like really good with computational methods, then get involved in projects and then try to expand on that. And the other thing I would always recommend is, there are a bunch of newsletters out there that are free to subscribe to, that are related to 3D printing. So what I always recommend is, have a subscription come in, and you can put in the keywords or topics that you're interested in. once on a weekend, for example. So I spend like a half a day or like a day in the weekend just trying to catch up on the papers and which company got acquired by whom, just making sure we're not missing, and also there you'll see a lot of cool applications. And the third one that I would say is it's not going to hurt to get started on programming, regardless of which field you're here from. It is going to, I think it's almost a given that, you need to have some programming expertise and some basic Python machine learning methods, regardless of the, experimental elements. So those three things was what I would say. One, play to your strengths, find project, be informed with newsletters and email blast, and get some Python and machine learning programming experience.
Great, thank you. Luke, did you want to go next? I saw you were.
Yeah, sorry, jumping at the bit for this one. So to build off the third point, especially, right? I mean, like cybersecurity is not going away, right? The whole digitization effort is not going away. So, no matter what field that you're in, at least learn to be able to speak the language back and forth, right? Get familiar with some of the terms, some of the vernacular, right? You don't have to become an absolute expert in everything. In fact, it's impossible. But just familiarize yourself with it because it's not going away.
That's great. And Joshua, did you have any closing remarks for the students of the future?
Yeah, I think increasingly systems engineering and kind of a system lifecycle based approach is going to become more important as we move into more unique kinds of devices. And initially cybersecurity was about securing operating systems or networks, kind of commodity items where you could count on one or two hands the number of different systems. But we're rapidly moving far away from that. There's all kinds of different machines and they're being configured all kinds of different ways and different kinds of supply chains. So rather than bolting security on after the fact and having it take as long as it has in the IT domain, we need to be more dynamic about getting there from the get-go. And I think we need to treat security like a non-functional requirement that supports the basic functionality of the system. So treat it like we would treat reliability or quality or maintainability or something like that. And there is established discipline on how to do that sort of thing. And I think we need to apply that more to security.
That's great. Thank you so much. So I'm just going to give a couple of concluding remarks now. Let me just share my screen. So hopefully you can see this. So I want to just thank again the panelists that came today. That's Professor Guha from Pennsylvania State University, Joshua from NIST, and Luke from Carpenter Additive. And to everyone in the audience, I'd love to invite you. Firstly, thank you for coming and joining us online. And if you're watching on YouTube, thank you for watching it through YouTube. Please join our next panel on May the 5th. And I'd also like to thank our organizers, Dr. Nikhil Gupta and Dr. Ramesh Karri, both here at NYU, Gary Mack, who's a PhD student here, and also the NYU Center for Cybersecurity and the National Science Foundation. So from here, that's everything for today. This talk's recorded and will be put up onto YouTube. And thanks again to our panelists and everyone else for joining and watching. Thank you so much.
Thank you.